Hi, welcome. In this video, I'm going to be taking you through the roadmap for you to take, or the roadmap that we're going to take in the upcoming videos on data science and machine learning with Python. So this one is just a slideshow of what I'll be covering, all the way from data science into machine learning with Python, all the way through it. So this tutorial is basically now the roadmap that we're going to be taking. So in case you're going to be following along the tutorial or the upcoming videos on data science and machine learning with Python, I would advise that you go through the whole of this video and maybe take down notes on the important areas or the sections that we're going to be covering, so that as we move on each and every video, you are on track. Additionally, I'm going to be putting this slideshow in the description video below, so that you can also have it, so that you'll be using to follow along, and you can also use it as a start point on your notes, so that you can be scribbling something along the way as we cover the specific sections. So now let us get it in there, and please, if it's your first time here, can you kindly please hit that like button, and also hit the subscription button, and the YouTube algorithm will be congratulating me for having you here. Otherwise, let us now quickly dive into it. First of all, we have data science and machine learning on our first page here. So let me just go to the next slide, and here, so when you're going to be studying data science, we're going to be covering several sections. So first of all, we're going to understand what data science is, what is data science to the core. So what is data science, whereby we will be understanding the fundamentals of data science, the intersection of data, the technology and problem solving, what technologies are used, and what kind of problems are we solving using data science. Basically, we're going to be looking into that on our introduction phase, so that we understand what data science is really about. Under introduction 2, we are going to be looking into characteristics of data science or our data scientists. So in case you are aspiring to be a data scientist, or maybe you already have a basic skills in data science also, this is going to be helpful. So we are going to explore some of the skills and the roles of data scientists in the company based level, and also at a freelance level. Remember, the skills that you're going to be getting here, you can apply them in real market. Also, you can do freelance on platforms like Fiverr, Upwork, and other platforms, depending with your with the area wherever you're going to get the work. Also, we're going to be looking into the type of programming language and the expertise that you need to be a data scientist. So basically, in this video, or in this series of the videos that we're going to be handling here, I'll be specifically doing them with Python, data science with Python, and then into machine learning with the same Python all the way through. Another thing that under introduction that we need to know for you to now start your journey in data science, in case you are a beginner in data science, is data science tools and workflows. So what are the tools that you're going to be using for the process of data science in this programming journey, or in this learning journey of data science? What are the tools? First of all, we are going to be looking into popular tools that are used in data science with Python. And the first thing that you must understand, because you're trying to talk about data science with Python, you should know Python. You must have basic skills and understanding of Python. Another thing you have to understand, you have to have the required tools like Jupyter Notebook, or you can use Visual Studio Code. I'll be using those that's called an integrated development environment. It's just a tool that will enable us to write our code and then test with the data. We get the data, we use the Python programming language, and we go ahead and now use these tools to visualize our data, or test our data, or do several things with the data. Another thing is, now we have to understand about open source libraries. Open source means just libraries or tools, another form of a type of tool that is readily available that makes your programming journey easy, because there are some of the activities or some of the computations that have been done before, and out of this computation being done severally repeatedly, we end up creating a library, we end up creating a tool that will enable this activity. When it's done in the future, it becomes an easy step, because it's already a step that has been done severally, and it is a step that many people are going to use. So we end up creating libraries that can be used by other programmers or other scientists to do the same, or to do certain computations. So we have open source libraries, and under libraries, if you are familiar with Python, I think you know basically what libraries are. If you're not familiar with Python, in the description below also I include a link to the basics of Python, from introduction to advanced concept in Python, because for you to be able to follow along the following sections that I'll be doing, the next videos of data science with Python, you need to have basic knowledge of Python, that you are able to follow along whatever we'll be doing in the preceding videos. So understand iterative process of data and of data science. So basically, under introduction, those are some of the 3 key areas that we're going to be looking into, and then we now be ready now to go into the next section, which will be Python basic for data science. As I've said, I'm going to include a link in the description below that will be teaching you Python basics for data science. All of them will be in the link below. But under Python basics, data types and control flows, that one it will be in the video. But now we'll be picking up from data manipulation, data visualization. So data manipulation will be using libraries like NumPy, Pandas. Remember I told you here we have open source libraries. So some of the libraries are now the Pandas and the NumPy, whereby NumPy is used for numerical computations. Basically NumPy came up or was invented by scientists who are trying to do very complex numerical computations, and that's why it is more of numerical computation, numeric numbers. But now Pandas was now invented, it's like built upon NumPy. You can't say directly, but it's like it came after NumPy, because basically they were businesses that came to realize like NumPy is a very useful resource, and now they decided to now modify and come up with something that will be able to fit into business models, and those business models can be using these Pandas to do data manipulation, study their data, analyze their data, and come up with useful information on the data to enable their businesses to grow. So some of the libraries that we're talking about is NumPy and Pandas. Those are the basic libraries that we're going to be using very often, every now and then, like all the time, whatever we're going to be doing data analysis with Python. Then another thing is visualization. When you're doing data science, one thing that you want to do is to present your data. You want to present your findings, and the easiest way to present your findings is by visualizing, by plotting graphs, by plotting bar charts, by plotting from simple to complex graphs. When you're given a set of data, you want to present to someone who doesn't understand anything in the data. You find giving them numbers, it will be very easy, hard for them to try to understand whatever is going on in the numbers. But if you present to them a chart or a bar graph or a line graph, be it pie chart, a pie chart can give you very deep information with just a single glance. That's the purpose of visualization. So you as a programmer, it's your work to deal with the technicalities, and then when you're presenting your data, you want to present in the most simple and understandable way. That's why we're going to be using visualization tool, which is called Matplotlib. Matplotlib, the short for that, but it is a mathematical plotting library, I guess. Yeah. So with that said, I think now you understand. You have to know that what is data science, then you have to understand basics of Python. Then after that, you're going to understand data manipulation, that is using libraries like NumPy for numerical computations and Pandas for data manipulation mostly. And then after you have done that data manipulation, you're going to understand visualization. You have to visualize your data, you have to present your data in a visual form. So under data manipulation there are other many tools, but those are the basic tools that we're going to look into and into other advanced tools. The next section, after now learning basics of data science and to the depth, to the core, now we want to look into machine learning, because you said these tutorials that are going to be following will be data science and machine learning with Python. So we can't do machine learning if you don't have data. So this is how it works. Machines are meant to learn, and for a machine to learn, it has to have information that it's learning from, like a kid or a human being. For you to learn something, you have to read. You have to read notes, you have to read books. So for machines now also to learn, they need something or books for them to learn. And what are the books that machines use? The machines use data. Now the machines use data like the company data, personal data, scientific data, like collected from the libraries, data collected from business organizations and all that. So with that data now is now when you come and do what? And train a machine or teach a machine using that data. But before you teach the machine using that data, you have to understand the structure of the data. It's like you have to understand what is inside the notes. As a teacher, for instance, if you're trying to teach kindergarten students on mathematics, like on a certain topic in mathematics, be it mathematics, any subject, you as the teacher, you have to understand what is in the book. Then you come to class and teach them what is in the book, what you have understood from the book. So that's how machines are. So for you to start training the machine or teaching the machine, you have to understand the structure of the data that you're going to train with the machine with, so that you can come up, or the machine can come up with resourceful information. That's why we do data analysis or data science. We understand the data, we manipulate the data and collect insightful information from the data. Now after we have understood our data, now we come into machine learning. Now the machines have to recognize patterns, pattern recognition, and AI concept. So after cleaning or collecting the data, understanding our data, knowing now this is the structure of our data, we start training machines. And then after training the machines, we have to ensure that the machines are doing the correct thing. That's why we do testing and validating the machines that we're going to be doing. So after data analysis, we're going to look into fundamentals of machine learning, and inside fundamental of machine learning, we're going to study pattern recognition. We're going to study training and testing phases of machines. We're going to look into biasness and variance and regularization. Remember, when you're trying to train machines, there is always some biased data, or there's always variations, and also we have regularization. So you have to regularize whatever information you're trying to teach the machine, so that it can build best models. So under training, you have to understand the importance of splitting the data into training and testing sets, and ensuring models reliability with cross-validation. What does this mean? It means for you to test or train and test a machine, first of all, you have to give it a certain type of information, and then after that, you have to test if it has collected the correct data. Take this simulation of a school also. When you teach your students, kindergarten or whichever level, when you teach them with the notes, you teach them with the information, you give them sample questions. After that, you have to test to understand if they understood what you taught them. Now you go to the testing phase. So you find a teacher can teach 10 pages of notes, but will test the students with 5 pages of notes or 2 pages of notes, questions from those areas. That's the point of testing a machine. And then after you have tested the machine, you cross-validate, you cross-check, are the outputs correct? Has this student gotten whatever I taught them correctly, or is there a problem? If you identify a problem, now that's when you go back. You try to tune, you try to fix, you try to adjust your model so that it can be able to produce the correct outcomes. And as you do this now, is what we call training, testing, and cross-validation to ensure that the accuracy of a machine is as high as it should be or it can be. The next part is bias and variance. Remember, there is biased data and there is also variations in those processes. We have regularization. You find there is a trade-off between values. There is a big gap between values. For example, there is a big gap between what you taught on lesson 1 and lesson 4. So what does that mean? You can't teach one concept here and then teach another concept that is at the end of the topic. You have to go through the process. So that's just an example I'm using. So that's the point of regularization. You have to try to make sure the information is as regular, is in the form that is expected, so that as the machine learns, it follows a particular pattern. It becomes easy for it to reference as it learns and becomes better. So that will be now the covering of machine learning fundamentals, whereby we do pattern recognition, training and testing, cross-validations, and then bias, variance, and regularization. Bias, variance, and regularization is just like the processes that enable you to improve the training phase, so that you can have a better testing results and accurate cross-validation processes. That's the point of bias, variance, and regularization processes. The next part, we're going to look into regression techniques. What are regression techniques? You have the linear and polynomial regressions. We have these two types of regression. Linear regression is like a model that assumes, or is a technique that assumes data is in a given straight-line pattern. It predicts in a linear form. But now polynomial regression is an advanced type of regression from linear. Polynomial is a regression that does not, the data is not necessarily linear. The data is not in a straight line, or it's not exponential. It's not growing in a given straight line pattern, but it is regular. Even though it is regular, the data is following a given pattern, even though it is not linear. So polynomial regression is like a curve. It follows the pattern of the data. The data doesn't have to be necessarily linear. So that's the difference between linear regression and polynomial regression. Basically, both of them, they follow the pattern of data, but linear regression follows a straight line, while polynomial regression now follows the pattern of the data. The data can be random, however, even though it is random, it is following a certain pattern. It's following a defined pattern, a pattern that you can see through. That is now the difference between linear and polynomial regression. That's why we're going to be looking into these two techniques and how they correlate and how they differ from one another, and also we're going to understand when to use linear regression model and also when to use polynomial regression model, or when to use both, or when to test both and see which one is going to give you important or insightful outcomes from the testing, training, and also cross-validation phase, so that your model can perform as perfect or as good as you want. But now in the process of linear and polynomial regression is basically studying the relationship between variables using linear and polynomial model for prediction. What does it mean when you say we study the relationship between variables? We have dependent variables and independent variables. So what do we do here? When you're using, for example, a linear model, you're trying to identify a dependent variable, and then you're trying to cross-check it against independent variables. So that's why you follow a certain pattern. There's a dependent variable that we're using, and then there's an independent variable, or a number of independent variables that you're trying to use, so that you understand the pattern in the data, so that the machine can learn through that pattern using the linear variable, or the dependent variable, to cross-check against independent variable, so that it can come up with a desired output. The same applies to polynomial models. despite the fact the data is not linear, the data is random, but this data, it is clustered against a certain pattern. It is clustered against a certain pattern. There is a certain pattern of concentration, even though it is not linear or in a certain direction. It can be random, but there is a concentration in a certain pattern. So you use a dependent variable to test, or use a dependent variable to check against independent variables, so that the model can learn the patterns in that variables, or the relationship between that dependent variable against independent variables. It can be another one independent variable or many independent, 2 or 3, depending on whatever you're trying to train or you're trying to test against, whatever you're trying to regress against. Now, when you're doing the linear and polynomial regression, I told you there are scenarios where you need to use linear, and there are scenarios where you need to use polynomial regression. Now you go into scaling and shrinkage. So what is scaling and what is shrinkage? When you're doing linear and polynomial regression, there is a possibility of you finding errors in your data. So what can cause these errors of data? Whereby you find there are some variables that are very sparse or dispersed. So what does it do? You scale the data. You scale the data to a certain level, so that all the data is as close or is as in the gap that you expect it to be, so that the machine can learn in a very uniform pattern. So you scale the data so that it can learn in a uniform pattern. Shrinkage, so that is techniques like standardization and regularization to improve model performance and prevent overfitting. So we have standardization, that is now regularization is like shrinkage is also called regularization, whereby you regularize the data so that it is in the desired gap or gap bridge, to avoid data that is too far apart, or the values that are very far apart, from affecting the model training process. So you are like trying to regularize the data of the machine to learn against the areas of concentration, areas where the data is really making sense. There are certain data points that are very random, very far, that to the point that if you try to train a machine with that data is not as useful as the data that you could have used, which has a very thin gap against the certain pattern that the data is following. So when you're doing linear and polynomial regression, we are going to apply the scaling and shrinkage. Scaling is standardization, standardize the data, and then regularize the data, so that the model uses a data that is in a certain stream, or studies the data in a certain stream, so that it can avoid overfitting. What is overfitting? Overfitting basically is a situation whereby the data or the model learns patterns in your data set to the point that it is no longer learning, it is cramming. Can you imagine teaching students, and then instead of them understanding what you're teaching them, they cram what you're teaching them? What will this result into? It will make them think only inside whatever you have taught them. They can't think outside the box. And we want this machine to learn from our data, and then when it has finished learning from our data, it can be able to go out there and predict data that it has not looked into, or data that is coming in as new data. So if a machine does overfitting, it's like we are saying the machine has memorized the data we used to train. So if you try to test data from outside, it will end up giving you wrong output. So we try to avoid overfitting in models. It's like the model has learned too much in the data, or it has learned in certain patterns in the data to the point that it is like no longer learning, it is cramming or memorizing the data. So we are going to be looking why do models overfit, and how to avoid overfitting, and how to prevent overfitting. And one of the ways of preventing overfitting is by scaling the data and also applying shrinkage or regularizing the data. Well, much more on that when we'll be doing the programming part of it, and then you'll be seeing how these two things correlate or hit into each other. Now the next part we're going to look into is clustering and classification techniques. So what are regression techniques? Regressions are more of regression is more of numerical patterns, but now clustering is more of categorical patterns. Now under clustering classification we have k-means clustering, we have group similar, whereby we are grouping similar data points into clusters to discover pattern. What is clustering? Let us say, for example, you have fruits, you have you have vegetables. Yes, for example, you have fruits and you have vegetables. Now you want to put these two types of plants or whatever products into two categories. You want to put them into categories, which means it's either the product is either a fruit or it's a vegetable. So if you are doing that, it means you are putting a number of fruits into one cluster and a number of vegetables into another cluster. So that is clustering. So you find linear regressions or linear technique, or sorry, regression techniques. I'm sorry about that. Regression techniques, they are talking of more of numbers, variables, numbers. But now when you're talking about now things like vegetables, you find a vegetable is not a number. It's like you're trying to look into these vegetables. Yes, they can be carrying a particular variable. You can say now let one represent vegetables and let two represent fruits. But now each of the individual components in there are not represented by any number. So what are you doing? You are clustering them. So that's where clustering and classification technique comes in. So so group similar data points into clusters to discover patterns. So you train the model so that it can understand certain patterns and then learn about decision trees and random forests. They learn about decision making models and their improved versions through ensemble techniques like random forest. So these decision trees learn the patterns that have been created from the clustering process. And then we have something like neighbors, k-nearest neighbors, algorithm, and logistic regression algorithm. And they used to explore classification algorithms for tasks like spam detection or sentiment analysis. So basically, clustering techniques are techniques used to study data that is more of clusters, data that is more of either a yes or a no, or a comparison between number or three variables. It's like a comparison. It's not a calculation. It's like a comparison. For example, you have a cat, a dog, and a rat. You are comparing these three. You see, but if you have number 1, number 2, number 3, it's like an exponential. It's like a continuous line. Like you're moving from 1 to 3. So it's like regression is like the same type of product. Now one product is 1, another product is 2, or let me say a building, 3 buildings. The first building has one room, the second building has 2 rooms, third building has 3 rooms. So when you're trying to draw a line of the relationship between 3, it is like it is improving, it is increasing. So it's a straight line that is going up. The first house is 1, the second, or whatever, if the first house is 3, the second one is 2, the third one is 1, it is a down facing arrow or line. So the point is, with clustering, is like you're comparing different variables. So you're just trying to compare them. But now with the linear, with the regression, it is more of a calculation. But now we also have logistic regression. It is a logic. We're not trying to calculate values. We're just trying to look into logic. So we have logistic regression under clustering and classification of techniques. So basically we have 2 major techniques, that is regression techniques and clustering classification techniques. So down here I think there's a note for you I put here. K-nearest neighbor algorithms, It's a simple yet powerful supervised machine learning algorithm used for both classification and regression tasks. It makes predictions based on the distance between data points. Yes. And then now here I outlined key differences between classification and regression techniques. So as I said, for example, the aspect for classification, when it comes to output or the resulting output, is either a discrete class label. It is a label. For example, we say vegetables or fruits. So it's either the product is labeled as a vegetable or it's labeled as a fruit. So if you train data using fruits and vegetables, then when you are in your testing phase, you feed in either a fruit or a vegetables, and the outcome will be either the model should predict for you if it is a fruit. If it is correct, then you say yes. If it is wrong, then you say no. So that's how classification works. For regression, there are continuous numeric values. It can be either moving up or down. And then you have nature of prediction. Predicts which class an input belongs to. So that's why it's called classification. So you are classifying products. For example, we are saying you are classifying vegetables. So it predicts the class. If it is a product is in the category or in a class of vegetable, it will put it in there, the vegetable. And if it's a product in the fruits, it will put it there. But now when it comes to regression, it predicts a specific value based on input. Take an instance, for example, we are trying to predict how much money a company will be able to make by the year 2050. What will that happen? What will happen here is that our model will predict a value, an exact value that it expects in the year 2050 based on the data we have trained it previously, based on the current data. Now it looks into the future. It gives you a specific value. It doesn't classify anything. It doesn't classify the output. It gives you an output based on the input that you put in. So examples of classification, we have spam detection. Is either a model can either predict if a message is a spam or not. So it's either classified as yes, it's a spam, or no, it's not a spam message. Image recognition, you can recognize if it's male or female, or if it is, for example, you are trying to detect if this is Jonathan. It is either Jonathan or it tells us it's not Jonathan. So it is either categorizing as a yes if this is Jonathan, or a no, this is not a Jonathan. We have disease and diagnosis. So most of them are used in disease classification. For example, we can classify is this person sick or this person is not sick. Or for example, if someone you're trying to test if they are suffering from anemia, model it can either say yes, they're suffering from anemia, or no, they are not suffering from anemia. Or C, it can classify yeah, he is healthy or he's suffering from another disease, whichever the output. But it is comparing, it is coming up with a certain class of output. And then when it comes to regression, it can be used to calculate price prediction. Yeah, as I said earlier, you have stock prediction and all that. When we are doing classifications, we usually use evaluation metrics. What is the meaning of the term evaluation metrics? Evaluation metrics is the process of testing how our model is performing. So when you are doing classification, when you are trying to train a model, for example, for image detection or image recognition, you won't expect someone to be using regression model. You expect them to be using classification model. And if you're trying to do price prediction, you won't be expected to be using classification. You are going to be expected to be using regression model. This is where now you try to identify which type of problem you have and which type of model or technique are you going to be using in your model development. So here is where it comes in. So classification, when you're doing a classification model, you're trying to develop a model in the classification field or category. The evaluation metrics or the process or some of the forms or styles that you're going to use to test the accuracy of your model is using, we call it accuracy. We have accuracy of your model, we have precision, and then we have recall and F1 score. What is F1 score? We'll be looking into that as we are doing the programming part. You'll be seeing how we're going to be calculating the F1 score, how we're going to be calculating the recall and the precision. So please make sure to stick around in the proceeding sessions, in the proceeding sections, so that you can be able to grasp all of this and also learn how to apply them in your personal project, freelancing market, whichever area you have, be it if you are a beginner in data science or you already have concept in these areas. Be my guest, please, and make sure to hit that subscription button and like it if you feel this one is really helpful for you. And please, now I want to talk about regression. You have when you're testing the accuracy of your regression models, you're going to be looking into mean squared error, you're going to be looking into root mean square error, amongst other r squared error. We are going to be looking into all those. Now, when you're talking about key differences when it comes to the type of algorithms you're going to be using for classification and regression, we have this a key difference I want you to see here. For example, under classification we use logistics. It is logic. Remember, this is not a value, so you're trying to classify something, so you just use logic. It's like saying, okay, according to my logic I think this and this is correct, but this one is not this. So we use logistic regressions. But for regression model we use linear regression. That's the mark that difference. And then we have for KNN algorithm we use for classification in classification techniques. But when it comes to regression techniques, we use KNN for regression. So it is the same algorithm, but each technique uses different methods inside the algorithm. And then we have random forest algorithm. Also, it is used for regression in the regression category. And then we have support vector machines. So inside, when you are doing about when you are doing classification regression, mark this. Look at, we have support vector machines when it comes to classification techniques, but when it comes to regression techniques, we call it support vector regression. That's the key difference between vector machines and vector regression. So support vector machines for classification and support vector regression for regression techniques. And then you have decision trees, but still we are using the regression techniques. When it comes to classification, when you're using decision trees, we use decision trees for classification, support vector machines for classification, logistic regressions for classification. When it comes to classification, when you're talking about regression, we say we use linear regression, we use KNN for regression, we use random forest for regression, we use support vector regressions for the regression processes, also decision trees for regression processes. So as I've said down here, the key difference between classification and regression lies in the type of output or prediction that each method produces. Classification involves predicting discrete labels like yes or no, discrete labels, or while regression involves predicting continuous values or actual values like prices, temperature, and all that. Now after that, now these are the techniques that you're going to be using when you're training a model, either classification, if your information is about maybe hospitals or diseases, all of that, or if you're talking about values, price prediction, economy, or all of those, you're going to be looking into regression, linear regression, regression models. Now we have dimensionality reduction. What does dimensionality reduction mean? It's the process of reducing the number of input variables or features in the data set while preserving as much important information as possible. The goal is to simplify the data set, making it easier to analyze, visualize, or use machine learning models without losing crucial data patterns or structure. That one is a pretty long statement for someone to just process in one, but I'm going to simplify as much as possible. Dimensionality reduction. Look at this in this way. Look as information in the structure that information is not one dimensional. Look at information in the form of two-dimensional. Example, look at information first of all in one dimension. For example, you have a dot, a single dot on your paper. If you have a single dot, for example this one right here, just look at it in one dimension, sorry, in two dimensions. So this one is a two-dimension dot, or let me say this blue here. So this one is first dimension, second dimension. Now look at this information in a three-dimensional interface. So this one will end up becoming a plane, like a sheet of paper, or a piece of wood, a frame of wood. So that will be a three-dimensional piece of wood. But now can you look at it in a four-dimension interface, and five-dimension interface, and six-dimension interface, and seven-dimension, as many dimensions as you can, or you can think of which inside the data set, when machines are learning, there's a possibility of as many dimensions as they can be. But now when you're trying to train a machine, when the dimension increase, there are high chances the structure of the data is going to be fucked up, or is going to be messed with. So what do? We try to do dimension reduction. We reduce the dimension. We try to preserve the data, but make sure it is in the most simple form, so that we can be able to visualize the data. We can also be able to train the data successfully, or in the most convenient way, so that the data does not overflow or does not cause what we call noise, a lot of noise. So what is a lot of noise? When a machine is learning, the data tend to have certain patterns that are not in convergence, are not positive, are not helping it to improve positively. So that is some sort of noise. Assuming it's a class you're trying to teach people, and then there's some sort of noise, some sort of ramshackle here and there. It's like a real class simulation mode. Like, can you just think of a class? Those problems that you can find inside a class when you are a teacher, for instance, it's just the same thing that happens with machines. We have retardedness. Maybe sometimes it doesn't understand what you've just fed it. Sometimes it just, classmates are disturbing, the patterns of the data are not consistent, or maybe you didn't teach as much as you thought you have taught the student. That's what happens with the machines. So it tries to minimize the dimensions of the data, so that the machine can learn more effectively. Then after that, we're going to be doing models. We'll be doing with you people. We will build a model. Another thing, I'll show you where to get sample data for you to use, free data for you to use in your own models, as you're going to be doing your own project on your own. Even after the topics, after you have understood ABCD, I'm going to show you where you're going to be getting free data sets for you to use on your models as you venture into the future, as you look into more advanced concepts on your own. If that's okay, I'm going to show you where you're going to be getting those data for you to be able to do more projects, create your portfolio on GitHub or on GitLab. It depends with your preference. So that's it. The next section, we are going to look into support vector machines. As I've said earlier on, support vector machines, I guess I pointed out here, we have SVM, support vector machines, and then we have support vector regressions. So support vector machines are used to learn about separating data using hyperplanes and applying SVM for predictive tasks. Look, what is a plane? A plane is like a three-dimensional thing. It's a piece of a plane. Can you imagine a 3D thing? Can you imagine a cube, and you want to slice a plane out of a cube? So how will you do it? You'll have to slice two parts so that you can come up with a plane. So a support vector machine and is used for classification and regression. So support vector machine can be used either for classification, as we said earlier, or a regression technique can use support vector machine. So we are going to be learning about separating data using hyperplanes. So we assume a three-dimensional data sphere or data scope, whereby for us to do a certain for the model to learn a certain pattern, it has to follow a certain curve or a certain pattern or a certain line inside the plane. Just assuming it was a two-dimensional data sphere, whereby it's either x or y. So if it's x or y and you're trying to learn pattern in the data, you're going to be seeing on the paper, if for example you have plotted points on a paper, you're going to be seeing a certain line along the paper. So you're going to draw a line based on where the data points are clustered, or there are a lot of data points. So that is like for a two-dimensional plane, whereby we can see this where the data is clustered. We just draw a line through the clustered area. You just draw it, for instance. But now can you imagine, now we have now a three-dimensional space like a cube, and inside that cube there is data, and this data a machine has to learn from it. So you can't just take data along a certain line. You have to find the most optimal line or plane, most optimal two-dimensional area across the cube, either horizontally, vertically, or in an angle, whichever way that you're going to find the optimal data points. And then the machine is going to be able to do what? To learn to identify that as the hyperplane, or the optimal plane area where the data is as maximized as possible, so that the machine can learn through that, and then in the end it will be able to do predictive positively. So we say we learn about separating data using hyperplanes inside the three-dimensional, four-dimensional, or whichever dimension, and then applying these support vector machines for the predictive tasks. And the support vector machines, you have the predefined library, and you're going to be learning how to use that library effectively to give us these desired outputs. The next part is the use of kernel tricks to handle complex nonlinear data relationships. So kernel methods are techniques used in SVM to handle nonlinear relationships. So you find in SVM, when you're trying to collect to do an SVM data collection, or train a model in an SVM, if the data is linear, it just trains. But if data is non-linear, this is where, okay, we're going to be looking at the technique of how we identify if our data is linear or not linear. When you're writing the code, you're going to be visualizing your data points and understanding the patterns in your data, and this will be able to help you identify when to use kernel methods and when not to use them, where to apply and where not to apply. So kernel methods are techniques used in support vector machines to handle nonlinear relationships between data points. Remember, we said earlier on in regression, here we talked about linear regression and polynomial regression. Linear regression assumes the data is in a certain pattern, straight line pattern sort of. But polynomial regression is the data that is not straight, it is not linear, it is random data, but at least it has a certain pattern. That is the point of polynomial regression. So linear regression, polynomial regression is an improvement of linear regression. So now when you're talking about support vector classifications, this is where we assume data is in more than two dimensions, like a three-dimension data plane, whereby we have to identify a certain stream or a hyperplane, optimal plane, optimal area, or optimal three-dimensional area where the data is optimal for our machine to use. Now, if that optimal area is a curve that is not linear, we have to apply certain concept, for this case kernel methods, that will enable the support vector machine to be able to understand the relationship between the data points. That's when now we also talk about kernel trick It's the mathematical method used to implicitly map input data into the higher dimension. Okay, kernel trick is just a method inside kernel methods that is used to enable us to do the process. It's a mathematical method. You're going to be looking at the method itself when you're doing the coding, and you're going to be revisit this part of the explanation for you to understand even better. But basically, I want you to understand support vector machines are used for classification and regression techniques, and they used to also do the regression in more than one dimensional data planes, whereby it's a 3-dimensional data plane, for example, and it tries to identify an optimal plane, which we call hyperplanes. The keyword is hyperplanes, and then it applies this into for predictive tasks. Once it identifies the hyperplane, that's where the machine learns the data through that, and the most optimal data in that area. And then when the hyperplane has been identified, the second thing you want to look into is the hyperplane a linear or an nonlinear data plane. If it's a nonlinear data plane for this case, or it's a nonlinear hyperplane, nonlinear, not linear, not in a certain line. If it is random, some sort of random, now you apply the kernel method so that the class support vector machine can learn successfully. But if it is a linear, you don't need to apply the kernel method in that case. So that's how you should understand support vector machines. So after that part, we'll be looking into Scikit-learn pipelines, and we're going to be looking into workflows and automation. This one I'm going to be doing on GitLab or any other process. So streamline machine learning workflows by chaining processes, step and model training using pipeline. This basically just try to, now after you have understood data collection, data manipulation, now we have understood training, we have understood developing our model. Now after some time you reach a point whereby you want to just make sure whenever you have this type of data, this type of machine, you automate the process of training, all of those things. So you're going to be learning how to automate your workflow, and you find most of the companies expect you to have this skill, automating workflows, because you want to be repeating the same thing every now and then, so that whenever new data comes in or whenever new model comes in, all you focus on is some other things, is the things that are new. But if something it has already been done before, you just want to make sure you're just automating the process and maybe just triggering several areas or improving certain parts of your code to be able to fit in with these predefined models. And then you also have model pipelines that will combine data preparation, feature selection, and model building into a single reusable framework. What is a framework? A framework is like you have created, it's like now a notebook. When you are in class, you're being taught, you create your notes. If it is a mathematics or a chemistry unit, you create your notes that you're going to be, it's a framework that you're going to be using. It's like a framework for you to use. If you do your cuts, the results come back, there are questions that you failed, what do? You go revisit your notes. If you are preparing for the next exam, what do? You go revisit what? Your notes. So that's like a framework that helps you to learn through the process. So that's the point of model pipeline. Combine the data preparation, feature selection, model building into a single reusable framework. So you're going to be looking into that. How are you going to be developing such a model? We automate our workflows, and also we are going to be combine all these processes. We create a pipeline that prepares data, it selects certain features, it builds a model into a single reusable framework, and this framework is going to be very excellent, and also it's going to practically prepare you for the work environment. Even those who are already working, this is going to be very useful. It's going to help you even improve your skill in the area or whichever. If you find this useful, please make sure to follow the next parts of my videos, because I'm going to be diving into each and every of these sections to the core, to the best of my understanding, and you will really find this useful. I bet you that. If you don't, then make sure to hit me up. Next part we're going to look at data science and machine learning with an emphasis on how they intertwine. So I've literally taken you through the process of whatever we're going to be covering in the future videos. But now I want you to understand these videos are going to be covering two sections, data science part and machine learning part. So how are they correlated? So which parts are specifically for data science and which parts now venture into machine learning? So I created a table like here. So we have data science focus. Which areas are going to focus on data science? We have the foundation concept. So things like data science, workflows, tools, skills needed for data scientists. That is the introduction part. And then we have data manipulation and analysis, whereby we do introduction to Python basics, we look at Pandas, NumPy, and then we look at visualization, and then cleaning of the data, organizing and analyzing data. After that, we're going to looking at clustering and regression. Clustering and regression techniques like regression and clustering, which are enable us to understand the patterns in the data or relationships for the data points in our data, given data. Now the machine learning part basically will be focusing on machine learning fundamentals and then advanced machine learning techniques. And then we have practical applications, whereby we say we're going to be learning how to apply the machine learning algorithms like k-means, logistic regression, and all that. Finally, how do the both of them correlate? So data science as a foundation, establish the data science. We are going to establish data science as the basis for the processing, pre-processing and understanding the data in ML workflows. So the data science part enables you to understand data, understand how to handle data. It's like you are reading notes. It's like you are the teacher. You are trying to understand what is in the textbook. And then after that, when you're going to machine learning, you already know what your data is about. Now you're going to train machines based on your data. For example, after the data understanding part, the data pre-processing part, it's like you've understood the notes. Now you are able to identify, am I going to be applying clustering techniques, or am I going to apply regression techniques, or am I going to apply both in this scenario? So it's like you have understood the notes, the syllabus. Now you're going to put it out there in a machine. You're going to teach that machine. You already understand what is in the data. So that's the why it is very important before you go into training a machine. You understand your data. You understand what is my data, what am I trying to achieve with this data that I have, which models or which algorithms are going to be suitable for this data. So that is how the two parts correlate. So without further ado, I guess I've pretty much covered each and every area that I'm going to be covering with you guys in the next sections. So as I said earlier, this PowerPoint presentation I'm going to include in the description section of this video. Alongside also I'm going to include PDF of the syllabus or Python for machine learning in the notes section for you to be able to follow along. Another thing, I'm going to introduce to put a link to the video to introduction to Python or basics, everything you need to know inside Python in the link or below or in the description below, so that you'll be able to grasp basics of Python. Then when you come, you're not going to be diving directly into now data manipulation or starting the data science part as fast as possible. See you there, guys. Thank you for watching, and please hit that like button and thumbs up if you enjoyed this, and please, if possible, can you just introduce this video to a friend and a friend to another friend, that we can grow or we can build the YouTube algorithm. Thank you, and see you around in my next video.